Okay, looks like there's a few more people coming on here, so looks like we'll get things rolling here. So once again, for those of you who have joined us here, I'd like to welcome everyone to this special webinar on energy savings and green considerations in motion control. My name is Miles Budimer. I'm the senior editor with Desireorg magazine, motioncontroltips.com, and linearmotiontips.com. And I will be the moderator for today's webinar. And I'd like to start by saying that perhaps not everyone who wanted to join us here today could be here. So if you would like to, you can tweet about this webinar today over at Twitter with the hashtag GreenMC. And so that can kind of keep other people who maybe couldn't join us here kind of informed about what's going on. And also, I'd like to remind everyone that you can post questions throughout this webinar for both of our presenters using the function that's built into the GoToWebinar software here. So you can post them throughout the webinar, and we will get to the questions at the end of the presentation. So right now, I'd like to introduce our presenters for today's webinar. And first we have Ken Kearns, who is the Marketing Programs Manager for the Motion Control and Low Voltage Drives Unit at Siemens. Ken has been with Siemens for over 19 years and has held various roles there, including application engineering, project management, and marketing as well. He's also responsible for the variable frequency drives energy efficiency programs. Ken holds a Bachelor of Science degree in Electrical Engineering and a Master of Science degree in Technology Management. And our other presenter is Jesse Henson from Baldor, who's a member of the ABB group. Jesse presently heads Baldor's motion control sales in North America. He resides on the board of directors for the Motion Control Association, which is dedicated to promoting the understanding and use of motion control technologies. Jesse began his career with Baldor back in 1997 and has been in several roles there as well, including general management, application engineering, sales, and service of motion controls for well over 14 years there. So it's safe to say that our presenters bring a pretty healthy wealth of industry knowledge here, which they will share with us today. So to kind of get things going here, just a tiny little bit of background here. So what exactly does green engineering mean in motion control or in a motion control context? I think most of us probably have heard the term green before someplace, probably to the point of that we don't want to hear it anymore. So we know kind of what it means when we talk about things like green energy or alternate fuels, or even in the areas of kind of everyday life, such as recycling in your homes, plastics or bottles or cans or that kind of thing. Hybrid cars use less fuel, those sorts of things. But what exactly does it mean in the world of motion control? So today, what we're going to do is talk about several topics within that world. Particularly areas that deal with energy savings. So some of the things we'll look at are variable frequency drives, or VFDs, and how they can help in saving energy, particularly in the world of industry, where up to 1/3 of the total energy consumption in the U.S. takes place. It's a pretty sizable chunk. In fact, I think it's the biggest chunk of energy usage here in the U.S. We'll also look at different types of motor technologies, for instance, induction motors versus permanent magnet motors, and we'll also look at some aspects of the Energy Policy Act, which is recently passed, and also how that act is helping to drive some of these trends here as well. So without any further delay here, let me present our first presenter, which will be Ken Kearns from Siemens. So Ken, the floor is yours.
Thanks, Miles, and welcome everyone. Well, let's jump right in. As Miles said, I'm going to talk a bit about energy efficiency and motion control using variable frequency drives. And just by way of overview here, as most of us are aware, and Miles kind of alluded to there, effective energy management in industry is becoming increasingly important. and primarily due to drivers such as rising energy cost, government regulation, product and process reliability, and things like environmental responsibility, as we all know about. Also, most of us understand already that energy efficiency in production processes plays a decisive role in increasing the productivity in a given facility, which consequently will improve the business's competitiveness. But the question is, how do you get to the point of understanding and achieving the energy efficient goals of your operation? What I hope to do with this presentation is kind of give you a good starting point. And that being said, today we'll discuss an effective approach to achieving your energy efficiency goals with motion control systems. First, we'll talk about the energy efficiency circle, and with the 3 phases or stages within that process to help you achieve your energy efficient requirements. Secondly, we'll briefly touch on energy consumption and the associated technologies in industry today. And then finally, we'll look at variable frequency drive systems and energy efficient motion control. Well, the concept behind the energy efficient motion control systems is one that's not new. The process itself is similar to continuous quality improvement that we're all probably familiar with. The idea is to evaluate the entire motion control system from input to output, and the point there is to optimize your energy requirements. Well, to do this, you can subdivide the energy efficiency process, or in this case, the energy efficiency circle, into 3 phases: identify, evaluate, and realize. Effectively, as with any quality system here, the optimum efficiency comes as a result of continuous improvement. This is a never-ending and ongoing process of constantly monitoring and improving in order to achieve the most optimal energy efficient system. And to provide just a little more detail, we'll look at each of the 3 phases. But first, as I mentioned in our previous slide, there are 3 phases there: identify, evaluate, and realize. In the identify phase, the energy consumers are basically discovered. That's where you go out and say, hey, I've got this machine, this application on this machine is using X number of kilowatt hours or whatever. And then in the evaluate phase, that's where you actually analyze it, take some measurements, do some calculations, and actually begin to realize what the potentials are. And then in the realize phase, the solutions are basically implemented. And once you begin to realize those solutions, you move back to the identify stage, and it just basically comes full circle again. And again, I have to emphasize it's a continuous effort of identifying, evaluating, and realizing. In the identify phase, it primarily involves discovering the different areas where energy is consumed, with the objective of transparently showing the energy requirements of the various sub-processes. What this does is it allows for an initial evaluation of the potential energy savings, and then additionally it allows for the creation of the basis for some intelligent and efficient energy management. Effective monitoring here is indispensable during this phase, and especially when it involves complex tasks as we see in motion control systems. It's only with effective monitoring that the relevant variables can be precisely analyzed. And a few examples of those would be obviously electric power consumption, but also load profiles, temperatures, flow rates, and those kinds of things. In the evaluate stage, what we want to do is understand where the potential savings are. And once the energy flows have been captured and evaluated, and the largest energy consumers have been identified, is when you begin this evaluate phase. So in short, the evaluate phase means that you perform the calculations at all the levels of the process to basically analyze and estimate the energy use, not just electrical, but mechanical, especially in motion control systems. The evaluate phase involves actually determining the specific elements of energy savings, and what your potentials are there. So when we move to the realize phase, which is the third and the last element of the energy circle, this happens once after you've defined the optimum measures based on the economic analysis and evaluate phase. You want to begin to realize the savings potentials that have been determined to be the most effective, obviously, through the implementation of energy efficient changes to your system, whatever that may be. With motion control and drives, obviously, special emphasis is given to the variable speed drive portion of that. And if you look at drives overall, drives represent about 65% of the industrial power consumed in industry. And Miles mentioned it earlier, industry consumes about 31% of our energy, well, between 31 and 35%. So 65% of that energy is being used by electric motors. In some cases, the energy cost can be cut up to about 70%, believe it or not, especially with applications that use the affinity laws of flow type applications. And if you look at returns on investment, in some cases, it can be as low as 3 to 6 months, depending on the application. This not only applies to new plants and system installations, but it also applies to retrofits as well. Now let's look at some of the areas where we see major energy consumers in industry today. If you look at industry today, it consumes, like I said, about 1/3 of the energy in the U.S. It's basically consumed in 5 areas. You can kind of cluster them together: power quality and consumption monitoring, lighting, steam, gas, compressed air, water, networking, infrastructure and control, and then motor control centers, and the big one for us today, VFDs and motors. For the most part, we're going to focus on the VFDs for this particular presentation. Well, if you look at VFDs and energy efficiency, there's really 2 categories you can divide the types of energy savings we see into, and that's flow control optimization, which is pumps, fans, blowers, and compressors, and then wasted energy recovery applications, which typical regenerative type applications. You see quite a bit of this in motion control systems. But I don't want to negate the fact that flow control applications are valid applications as well on motion control systems when you think about the entire system, which is the intent of this presentation, is to try to make focus on the entire motion control system. There are also a number of other areas you could look at, and we'll take a look at those in the next couple slides. But first, let's talk a little bit about why we want to use VFDs. And this kind of summarizes the overall approach and reasoning behind using VFDs. Many of them are just kind of common sense. Obviously, they save energy, reduce electricity. If motors represent 65% of the power demand in industry, that's a really good place to start looking for energy savings opportunities. Motor-driven systems offer one of the highest potentials for energy savings, about 70% in some applications. Almost all the motor life cycle cost is expended on the energy the motor uses. That sometimes has a tendency to be one of the barriers because of the initial financial capital outlay that has to come up front on installation. But if you look at the overall life cycle and cost of a motor, by far the amount of money spent on that motor is for the energy use. Also, government incentives, utility rebates, and savings-based financing can provide low upfront investments, and we've seen, like I said, ROIs in as few as 3 to 6 months, depending on the application. And what's really surprising to me, based on a Department of Energy report published several years ago, approximately 33% of industries report absolutely no improvements for the basic, what we call low-hanging fruit, pumps, fans, and compressors in the facilities. So again, opportunities to look for when you're trying to find energy efficient and energy savings installations. What are some of the benefits of implementing energy efficiency VFDs? Again, some of these are fairly obvious. They save energy, they reduce utility bills, provide precise motor speed control. That's probably one of the major things we saw up front with the initial development of variable frequency drives is the actual capability of controlling the motor speed very precisely. Also improve the overall process control, and they reduce operating and maintenance costs. May require a little upfront investment. They're fairly easy to implement and have payback times of less than a year in some cases. And last but not least, energy efficient VFDs help reduce the negative impacts on the environment. They are considered energy efficient installations, and they do qualify for government and utility incentives. Let's, as I mentioned a few minutes ago, there are a number of areas for energy savings in VFDs in motion control applications. This graphic kind of represents some of those. The slide following this has a few more detailed items on it. But one of the primary ways we see energy savings with VFDs is through regeneration of wasted energy. What happens is the drive is capable of taking energy that's normally just wasted either via inertia or braking and return it back to the power grid in a facility, or more commonly if you have multiple drives and motors on one system and you arrange them with a common DC bus arrangement, the regenerated power can be recovered for use in other motors in the system. Another way that we can see energy efficiency with VFDs is via power factor control. For example, an active line module can automatically compensate for any reactive power, whether it's inductive or capacitive, in the system, and give you a near unity power factor in a lot of situations. And also the automatic compensation for harmonics. Active line modules can do that as well. They automatically compensate for any harmonics on the grid side, and the result obviously is that the distortions on your AC voltage are prevented, which prevents losses from non-sinusoidal voltages. Now let's take a look at a few more areas that can be focused on. I mentioned the regenerative applications, but here's where I mentioned pumps, fans, and compressors a little bit earlier. The ancillary systems on motion control systems, where you typically don't look if you're thinking about motion control, but that's part of the overall system as well. There's opportunities to save energy there. So if you're looking at say pumps, for example, that have some sort of mechanical control, a valve or a throttle or something like that, if you eliminate the mechanical means and just use the drive to control the flow, obviously there's energy savings to be had there. I mentioned the power factor monitoring, which obviously equals less energy consumption. Also, control and monitoring systems. We see more and more now that customers are going to a thin client control system versus PCUs, which basically means just less power consumption and also less heat in many instances. The next one, obviously, heat dissipation for power units. The more efficient you build your power unit, and the less heat it creates, the better off you are, or if you are able to dissipate that heat in an efficient manner, then obviously it's less energy consumed as well. One of the big areas we see some difficulty in is the use of proper component sizing to avoid oversizing. And quite often, just because of uncertainty, we'll see drives and motors that are oversized just out of sheer uncertainty about whether the actual motor and drive will be able to handle the application. And then finally, mechatronic evaluation for optimized system efficiency. It takes a look at the entire system mechanically and electronically, which equals less energy consumed as well. Well, I think we've made it to the last slide here for me. Here's just a list of important links Don't try to write them down or anything now, but this presentation should be made available for you after the session, and you can just take an opportunity to go to each one of these sites and check them out. Thanks for your time, and Miles, I'll hand it back over to you.
Okay, Ken. Thank you very much for that presentation. And let me just add two more brief points here. That one is that, of course, during any time during this webinar, you can post questions for either Ken or Jesse, and we will get to those questions at the end of the webinar. And then also, secondly, as Ken just mentioned, that you don't have to write down all of those websites there that he had just showed in that second to last slide there, because everybody who's registered for the webinar should get a copy of the actual slides here. So all this information will be sent to you. So, and with that being said, then let me turn it over to our second presenter, Jesse Henson from Baldor. So Jesse, take it away.
Good afternoon, everyone. Today we're going to discuss going green with motion controls. When we talk about motion control, it really involves a lot more than just the motion controllers by themselves. Although motion controllers are a big part of it, we also include the servo drives and servo motors as part of a motion control system. The idea today will be to discuss topics that many manufacturers of equipment are looking at to produce an overall more energy efficient system. We will look at induction motor efficiencies compared to permanent magnet brushless servo motors, discuss the Energy Independence and Security Act and how it will impact motion control. We will then look at how using DC shared power for your servo drives can provide system savings, followed by trends using integrated motors and distributed power for overall system savings. Then we'll wrap it up with things looking at the entire system and how motion controllers can help save energy. The industrial market has a lot of challenges to compete in today's environment. Everything has to be manufactured for less, yet, we still have to produce a better product. Although this is great and go to have for the finished product itself, the drive to get cost out has found its way all the way up to buying the equipment itself. There are a lot of times when selecting components, we look at, will it do the task required for the application? And then who has the lowest price? This may work out great for component cost of the machine, but how does this impact the end customer that will be paying the cost of owning the equipment? This is where TCO comes in. TCO stands for total cost of ownership. As a manufacturer of end customer product, I must take more than just equipment cost into account. The challenges are how to reduce my overall manufacturing cost. We can do this by increasing throughput, reducing labor, reducing energy consumed by the equipment, minimizing waste, keep my equipment up and running with reduced downtime, and remove all things that are considered non-productive. These are all very important factors that are being looked at more every day. Some of you may be familiar with the Energy Independence and Security Act. The future of U.S. energy consumption has really caused a concern for the Congress, and it's been enough they've acted upon it. They passed the Energy Independence and Security Act of 2007. The impact of this act will affect everyone in the U.S. at some point. Some of the key points from the act are the automaker's gas mileage meet 35 miles per gallon by 2020. Along with that, light bulbs must have 25% greater efficiency by 2014. What is also covered are all general purpose motors 1 to 200 horsepower that were previously covered by EPAC. They must raise their efficiency levels to a premium efficient level. This on average is about 3% of an increase. This will have an initial impact on the cost to purchase a motor, but long term the total cost of ownership, TCO, will be less. For motors, the act went into effect December 19, 2010. This is really bringing awareness to anyone that's selecting products to be more efficient and look at the cost related to these motors. So let's look at the different motor technologies and how they compare. The chart on the left compares different motors and their efficiency. The scale at the bottom you can see is for 1 to 5 horsepower, and the scale on the left is for efficiency. As you can see, single-phase motors are the worst efficient, and brushless PM motors are at the top, being the highest efficient. And then right below that, you'll see the 3-phase Super E motors below the brushless BSM. Those are the premium efficient induction motors, which is part of what the ACT is. These are close to the same efficiency, up to 2 horsepower, but servo motors are more efficient than premium efficient induction motors when you get to the range of 3 to 5 horsepower. The chart on the right now compares the average motor weight of induction and servo motors. As you can see, the brushless PM motors have over 30% less weight than an induction motor. In most cases, it is much higher than 30%. If we look at an example of a 3 horsepower single-phase motor, weighs about 80 pounds. A servo motor of the same 3 horsepower is less than 30 pounds. That's over 50 pounds difference in weight. That's a pretty big difference. We are seeing customers go with brushless PM servo motors instead of traditional induction motors for typical adjustable speed applications, just for the efficiency and lower weight of the servo products. Servo motors really shine in adjustable speed applications, as the efficiency through the speed range is much higher than standard induction motors. For motion control applications that require 3 axes or more, a DC shared installation could save some cost. Most motion control axes start and stop quickly for optimal machine performance. When we stop a motor quickly, this is excess energy that must go somewhere. If every drive has standalone AC power, this energy is put through a resistor and turned into heat. That's wasted energy. What if we could take this wasted energy and store it to be used the next time a move is initiated? With a common DC shared installation, you can do just this. The picture on the right shows 3 servo drives connected together with one common DC bus. There is only one main AC feed that powers all 3 drives. However, there are capacitors still in each drive that can take what would normally be with a wasted energy and store it inside of these capacitors. So the next time that a move is initiated, the energy is pulled from the capacitors instead of pulling the energy from the main AC feed. This ensures optimal use of all the energy in a system. Additional savings can be achieved where we would require individual branch circuit protection to wire these 3 drives individually with AC input power. With DC shared, you only require branch circuit protection to the first drive. And you can see that there in the picture. This saves on circuit breakers or fuses, cabling, and component count. It will also save on design and build time while improving overall system reliability and use less panel space. All these add up to potential big savings. Get to the next slide. So let's take it a step further. Let's look at the trends in the market for possible additional savings. The picture on the left shows a typical control cabinet filled with drives. These drives produce heat, and the control cabinet must be sized properly to not overheat the drives in normal operation. We then need to connect the drives to their motors. For a servo motor, this would include power and feedback cable. So if you have 3 servo drives and 3 servo motors, then you would need a total of 6 individual cables going from the control cabinet to the motors. As you can see in the picture on the right-hand side, this adds up to a lot of cables under the machine. If you've done many servo installations, you'll agree that servo cables are not cheap. There are a lot of applications the control cabinet is only there for the servo drives. If the servo drives could be removed from the control cabinet, then we could all the heat, reducing the size of the cabinet significantly. So we take all that heat out of the control cabinet, then we could really reduce the size. With integrated motor technology, we can do just that. An integrated servo motor has the drive mounted right on the motor. This removes all the drives from the control cabinet, and most applications, your control cabinet will look more like the picture on the bottom right. As an operator station, and you would have the motion controller and any kind of small I/O blocks would be in the back of that. You can also see the cabling is daisy-chained, allowing for less cabling for the entire system. To do this, there is one master power supply that will power a DC voltage to each integrated motor. This now provides DC sharing advantages as we discussed earlier. In this example, there's also real-time Ethernet technology running in the same cable as the DC power. So both your power and your Ethernet connectivity to control each motor is all in the same cable. So if you only have one cable for both power and communication, then being that it's real-time Ethernet, then you can still provide interpolated positioning across all the axes. Some manufacturers have capability to connect local I/O digital inputs or outputs right from each integrated motor. And you can see that in the picture on the far right-hand side. At the end of the line, there is digital I/O connected right to the last motor. So this allows I/O where you need it, and it reduces the cabling required even more. For OEMs, that makes the same machine over and over. There's a lot of savings in the panel cost, and assembly time is drastically reduced. We've seen applications where an entire panel that could be anywhere from 1 meter by 1 meter be reduced down to a third of that by taking the drives out of the panel. So how can motion controllers save? It's becoming a standard now for motion controllers to use real-time Ethernet for communication for control of servo drives. It is also becoming a standard to use absolute encoders with programmable memory right in the back of the servo motor. Now you may say that's great, but how does this really help us when we're talking about going green? The problem has been all these components that make up a motion control system have grown in intelligence, but there has not been a way for them to talk to each other. When everything is connected with a digital link, like Ethernet, then the motion controller has complete visibility of the entire machine. Now a motion controller can see all the way down to what the motor is doing. The motion controller can monitor system activity to know that something is going wrong before it even happens. A weak encoder signal, for instance, that can send an alarm to a motion controller. The servo drive has started to draw more current than normal. The motion controller can track this. With Ethernet connectivity, the motion controller can then send an alarm to a remote PC that would alert the maintenance department of a potential problem before it happens. This allows a plant to fix things on their schedule and not on the machines. There's not much worse than a machine breaking down right in the middle of production. If this machine is a main feed, then the entire line could shut down. Another advantage of complete visibility of a machine is the possibility for remote diagnostics. Instead of waiting for the maintenance department to show up, they can connect with the machine from their PC and have a visibility of exactly what is happening. If you had a servo drive fault, then this would not be a problem. The motion controller can see the fault inside the servo drive and send it back to the maintenance department. The maintenance person could be sitting in the back of a plant, or actually could be sitting halfway across the world. Once you have Ethernet connectivity, it does not matter. We're seeing applications that typically would use one motor with mechanical linkages to make all the different axis work on a machine be broken out in favor of one servo motor per axis. An example, that may be if you had one axis with mechanical gearing to do 6 axes of work, be broken out to use 6 different servo motors. So that'd be one servo motor per axis. But in return, you remove all the mechanical linkages that made the system run. So overall power required is drastically reduced. When you add the motion controller, you have the ability to enable the servo motors when you need them. This removes all the wasted energy in the system. It also removes a lot of weight from the machine, making it a smaller footprint while increasing overall productivity. Another advantage, since you are direct drive and using servo-driven axis, is you will gain accuracy, which reduces waste. Remember we discussed TCO, total cost of ownership? While yes, we're paying more for a motor control system compared to that one motor that ran the entire machine, the overall gains by removing the mechanics, energy savings by enabling a motor only when required, and higher productivity of the machine do offset the cost. You can now connect entire plants together to have complete visibility of the plant. This allows you to optimize the plant for optimal gains and reduce overall total cost of ownership. Let's go back and look at today's industrial market challenges to compete. Every one of these has their own set of challenges to overcome. Motion control systems are key to increase productivity, reducing labor, reducing energy consumed by the equipment, minimizing waste, reducing downtime, and helping tie systems together to remove non-productive steps. Energy cost continues to rise, and the impact of day-to-day cost to manufacture product is becoming a larger concern. So it's not just put in an automated system and everything will get better. You must look at the entire system and bring in the day-to-day costs associated with it to bring down TCO, total cost of ownership. Although we've only had time to discuss a few topics today, hopefully you can see some of the motion control systems and the ways that they can help you in your application to be more competitive in the markets that you serve. Thank you. All right, Miles, I'll turn it back over to you.
Okay, thanks a lot, Jesse. And once again, I'd like to remind our folks out there that they can post questions for either Ken or Jesse in the questions field there. It should be on over in the kind of the right-hand side of your screen there. It's part of the GoToWebinar software. So once again, thank you, Ken and Jesse, for your time today as well. And let's start things off with a couple of questions here. One, I'd like to kind of throw a question in Ken's direction there. During your presentation here, you mentioned something about the fact about incentives from the government for basically getting implementing a kind of a greener system in terms of energy savings. Do you know what some of those are specifically, or yeah, maybe where people can find out some more about that?
Mm-hmm. Yeah, if you go to the Department of Energy's website, mm-hmm. They have some energy efficient initiatives. I will admit that the website's kind of it's a little hard to navigate, but you do a search on energy efficient motors or something like that. You can dig down into some of their motor surveys, and they've actually taken, I don't know, a survey of hundreds of different industries and looked at motor usage and types of applications, and they focus primarily on pumps, fans, compressors, blowers, those kinds of things. Like I said, it's kind of the low-hanging fruit. Mm-hmm. And they went through industry and did a complete survey and got some really good estimations. And some of those numbers that I pulled out, I've got from them actually. And the energy usage portion of it for the industry segment, and then what they do is you drive down into the industry segment and they look at the different motor applications. So again, it's on the Department of Energy's website.
Okay. Okay, that's good. Here's a question for Jesse actually too. Here in your presentation, you were talking about the fact that if you get rid of some of the more traditional linkages in motion control systems in favor of servo motors, so for instance, maybe one servo per axis or something like that, there's quite a bit of savings there to be had. do you know, like, number-wise, like what kinds of savings we're talking about? Are we talking about pretty pretty big types of savings, or just I was just interested in that as you were kind of talking about that.
It does depend on the application. So some applications will, of course, have bigger savings than others. I mean, you can go as simple as there's some conveyor systems out there that have one master mechanical line shaft. So when you power the system up, you have to always run every section of the conveyor at all times. But if you take that line shaft out and you put individual motors on it, and they could be VFDs or servo-based in this application, then now you only need to run the conveyor systems that you actually have product on. So it really allows you to optimize your system so that you don't sit there 8 hours a day and run conveyor systems that may not need to be ran. So in those applications, it could be very significant. But again, it comes back to the application itself. Sometimes in the packaging industry, like for what we consider to be a vertical bag filler, then those you'll have like a potato chip bag of just putting chips into a bag, let's say. A lot of times those used to be all mechanical links, and now they're breaking out to all servo, and it allows it to optimize the entire system to not only save energy, that becomes minimal, but the savings that you gain in productivity and the enhancement by going direct drive with the servo product, your productivity goes through the roof by 30 or 40%, to where that you save overall cost because of that, because it takes a lot less time to do the same thing to get the amount of product out.
Okay. Okay. All right. Good. All right. Let's see. Let's see. I think we've got a question here from one of our from one of the folks here. Okay. Somebody here a suggestion that I'll just read what the question is here. It said, could Baldor and Siemens look at the DOE website and put on their website the products that meet those DOE specs? Then it's then instead of having to look through the DOE mess, as he put it, we can quickly go to your website or your web page and quickly see what items you have that meet those specs. It's a pretty interesting thought there. Huh?
Yeah, that's a good point, and it's something I didn't put in the presentation. But our products are actually GSA listed, so it's the General Service Administration. So if you look at drives and motors for Siemens, they're listed for actually government use. So if you understand why the government operates, they want every new building they build, it's got to be efficient. They got a certain category for it. So in their schedules, they list those products, and it just so happens, well, Siemens has a GSA listed product, and some of our competitors do as well. So the schedule, I don't have it in front of me right now, but if you go like to the General Services Administration, you should be able to pull up the schedule for its power equipment. It's not very intuitive when you look at the title of it. You really wouldn't do this power equipment, and then under the subheading of batteries and power supplies or something like that, it's just where they put drives, the category for drives. So
Okay.
I don't know if that helps or hurts, but yeah, good point. But the problem with the federal government website sometimes is that they may change it, and then adding a link and trying to maintain it, sometimes it just, you get a dead link every now and then or something. So it's not that they list a specific catalog number there. They categorize certain products, and they call them adjustable speed drives. That's their terminology. And if you go to the Department of Energy website, they actually list several categories of energy efficient installations, but it's simply categories. They don't specify a particular product as far as on the drive side, as far as performance goes. They just kind of categorize it adjustable speed drive. and go from there. It's different with motors. They do categorize the motor side of it, yeah.
Okay. All right. Jesse, do you have anything to say on that?
Back up what Ken was talking about. We're seeing the same thing. It's really difficult to pull all that information out off of the certain websites, and especially when you talk about anything on rebates and that type of stuff, it comes down to the state. Every state has different types of rebates. Okay. So what I encourage to do is that if you would like more information, we do have a lot of information we can provide. I encourage you to go to our website and look at one of the local district offices and contact them, and they should be able to help you in your local area of finding additional information.
Yeah, I will, and I'll just add to that. If you're looking for incentives, and that's a good point, it is very much, I mean, even down to the local utility company, yeah, it's driven at that level. And there's a couple of decent websites. One is Desireorg. Some of you may have heard of that. Yeah, DSIRE.org.
Okay.
It's the database of state incentives for renewable and efficiency. It really started out as a solar energy effort, and it kind of evolved into this whole state-by-state list of the major utilities and the major incentives. It doesn't get down to the small municipalities, and that's where I encourage everyone, if you're interested in energy-efficient installations, installing variable frequency drives or anything for that matter, if you don't see them listed on this Desire.org, pick up the phone and call them, because most utilities, most municipalities have some sort of incentive or some sort of program. So anyway. Okay.
Yeah, that's a good point too. I think sometimes it might just be easier to start locally, basically.
Yep.
And then go from there. Because I know, trying to access any type of federal government, either website or agency sometimes is daunting, just to put it mildly, I guess, right?
Yeah, very much so.
Yeah. Okay. Another question here. Earlier, when you were talking about this is for Ken, I think. When you were talking about, you mentioned some figure about 33% of industries reported no improvements for pumps and fans. I think those types of setups. I guess I wasn't clear about what that actually meant. Did that mean that they had tried some type of energy-saving systems and didn't see any type of improvements, or was it just that those systems hadn't yet been looked at yet?
Yeah, that's a good point. It's a little bit unclear. The Department of Energy did a pretty extensive survey of different size companies, and their motor, several different types of applications, is all predominantly around the laws of affinity, pumps, fans, and compressors. And in their assessment, they actually realized they categorized these industries: large, medium, small. I think it's 5 categories, and just pretty consistently throughout, if you look at them and take an average across those industries, about 30%, 35% have done nothing, absolutely nothing. They've not even made an attempt to install any sort of energy efficient drive motor systems.
Okay, I got you.
Yeah, interesting numbers actually. It was done a number of years ago, back 2004, sometime around there. So it's a little bit dated. I don't know how often they do it. More than likely every 10 years or so. So it'll be interesting to see what comes out in the next survey, actually.
Okay. All right. Good. One more question then. We had actually, Jesse, I think you had touched on this point too, where you talked about that the Energy Policy Act there.
Right.
And basically what types of motors that touched on. I know that there are plans also for the DOE has put out some, or will be putting out some new standards for smaller horsepower motors that are supposed to take effect, I believe, in 2015 at all. I was wondering if either you or Ken knew something about that, or could speak to that at all, or.
At this time, I do not have much information on that. We've been really focused on, since the Act just put into place for the 1 to 200 horsepower, really focus on ensuring that everything that all of our products are ready to go for that. And of course they are,
Right.
but it's a matter of getting the word out to our customers and helping them get the right product selected and things.
Sure. Okay.
And that's the same here. Our focus has been primarily on the recently enacted regulations. So now I don't spend a lot of time with the motor guys day to day, so they probably have people looking at it, but I'm just not privy to some of that information.
Okay. Yeah, that's still off by a couple of years still. About it's scheduled to go into effect, I believe, sometime in 2015 or something around there. So that's still, it gives people 4 more years, I guess. But it's something else that's coming down the road. And I think those are supposed to get into some of the fractional, ratings up to I think 2 or 3 horsepower or something along those lines. So. All right, well, good enough then. If there aren't any more questions here, then I'd like to take this time then briefly to just to once again thank both Ken and Jesse for your time today, and also thanks to everyone who signed in and joined us for this. And I'd like to remind everyone, as you can probably see on your screen there, that this webinar can be accessed at our website here, designworldonline.com. And also everybody who registered for the webinar will also be emailed this webinar as well. And also there's some information there on connecting further with Design World, either through Twitter or our Facebook page or through LinkedIn as well. So if there aren't any more questions, then I guess we will just wrap things up here. And once again, thanks guys for your time today and for your help in making this a good afternoon of learning and knowledge.
Not a problem. Thank you, Miles.
Thank you.
Right.
Thanks, everyone.
Thanks a lot, everyone. Have a good day.